Hi, this is lesson 3.4b, the continuation for eigenvectors and eigenvalues. So just to recall one theorem that we saw last time regarding eigenvalues. If we have a square matrix A, n by n, then its characteristic polynomial and again, characteristic polynomial is the determinant of a minus lambda I, is a polynomial of degree n in lambda. And if you take this determinant of a minus lambda I, called the characteristic polynomial, and set it equal to 0, the solutions are the eigenvalues of the matrix A. If it's an nth degree polynomial, then the fundamental theorem of algebra implies that you will have n solutions, some of which may be repeated and some may be complex. So this is a corollary, is that determinant of a minus lambda I equals 0 has n roots some of them may be repeated and some may be complex conjugate pairs. So as you know, complex solutions of polynomial equations always come in complex conjugate pairs. So we saw a couple of examples in the exercises for this section. If you have a complex conjugate pair of eigenvalues, then the corresponding eigenvectors will also be a complex conjugate pair. So, and we can go back to the example that we saw in the exercises. If you have the matrix A, 1 minus 1, 1, 1, this matrix has the eigenvalues lambda 1 and lambda 2, 1 plus and minus I. This is what it means to be a complex conjugate pair, the same real part and two opposite complex or imaginary parts. And the corresponding eigenvectors is r times plus and minus I, 1, where r is all non-zero real numbers. Complex conjugate eigenvalues correspond to complex conjugate eigenvectors of the eigenspace. So when there are repeated eigenvalues, the situation is a little bit more complicated. Let's first define a concept that we will use to study this called the eigenspace. So if you take an eigenvalue of a matrix, the eigenspace is just a set of all of its associated eigenvectors. So if we take lambda b an eigenvalue of a matrix A, the definition is the eigenspace of lambda is the set of all eigenvectors corresponding to the eigenvalue lambda. And together with the zero vector. So as you know, the zero vector is by definition not an eigenvector, but when we are considering the eigenspace, we are going to throw that zero vector back into the set along with the eigenvectors to form a complete vector space, as we'll see in a minute. But mathematically, the way you would write the eigenspace, if you write it as capital E, it's the set of all the vectors in Rn, if A is an n by n matrix, such that AV equals lambda V, which is just the definition of what it means for V to be an eigenvector of A with corresponding eigenvalue lambda. So the main theorem associated with this definition is the fact that an eigenspace is a vector space. And more specifically, a subspace of Rn, as indicated by the word space. So proving that something is a subspace of Rn, as you know, consists in proving two things. First of all, that it's closed under addition, and that it's closed under scalar multiplication. So let's prove those two things one at a time. So first, that it's closed under addition. So let's take two vectors, v1 and v2, in the eigenspace. So these are eigenvectors associated with the same eigenvalue lambda. And we want to prove that the sum v1 plus v2 is also itself in E, so that it's closed. So we're going to take v1 plus v2, and to show that it's in E, we are going to left multiply this by A, and invoke the property that v1 and v2 are eigenvectors of the same lambda. Factor out the lambda. So we have proved that A v1 plus v2 equals lambda v1 plus v2. In other words, v1 plus v2 is an eigenvector of A. And so it's in E. So we've just proved that E is closed under addition. The second half of the proof, we'll just take a vector V in E, so an eigenvector corresponding to lambda, and C, an arbitrary scalar. Scalar multiplication C times V. To prove that this is also an E, we again left multiply it by A. We can float out the C. AV is lambda V, so lambda times CV. So we've just proved that ACV equals lambda CV. In other words, that CV is in E. So CV is an eigenvector of A with corresponding eigenvalue lambda. So E is closed under scalar multiplication. So because the eigenspace is a vector space, you can do everything that you do with vector spaces with an eigenspace. For example, you can find a basis for the eigenspace, and you can calculate the dimension of the eigenspace, which is simply the number of vectors in any basis for that vector space. So coming back to our discussion of repeated eigenvalues. As we saw in the exercises, many times you have a repeated eigenvalue, which means an eigenvalue with a multiplicity greater than 1. If we take this example of the matrix A, 4, 2, 0, negative 1, 1, 0, 2, 4, 3. So we found that the eigenvalues are lambda equals 3, which is a repeated eigenvalue, so multiplicity 2, and lambda equals 2. So repeated, and this is multiplicity 2. So the corresponding eigenvectors for lambda equals 3, we found that V equals R times negative 2, 1, 0 plus S times 0, 0, 1, where R and S are free variables. So they're real numbers, but not both 0. So in other words, the eigenspace associated with this eigenvalue of 3 can be written as all the vectors of the form R, negative 2, 1, 0, S plus S, 0, 0, 1, such that R and S are real numbers. And E is a vector space. Again, here we do not need to specify that they're not both 0, because in the case of the eigenspace, we add in the vector 0 once again. Okay, the other eigenvalue, lambda equals 2, is not a repeated eigenvalue. It has multiplicity 1. In this case, we ended up with V equals R 1, negative 1, 2. And so again, we can write the eigenspace as the set of all vectors R times 1, negative 1, 2, such that R is a free variable. Okay, so we notice here that the multiplicity of this eigenvalue is 2, and we have 2 free variables, R and S, to build the vectors. On the other hand, the multiplicity of this eigenvalue is 1, and here we only have 1 free variable in the eigenspace. So if we compare this to the other example that we saw last time, the matrix B, 4, 2, 0, negative 1, 1, 0, 1, 4, 3. This one is the only difference, but it's a critical difference. The eigenvalues are the same as for A, lambda equals 3 with multiplicity 2, and lambda equals 2 with multiplicity 1. The eigenspaces, in other words, the set of the corresponding eigenvectors, for the first one, we ended up having R times 0, 0, 1. And for the second one, R times 1, negative 1, 3. So here we have a mismatch. Even though this eigenvalue 3 has multiplicity 2, we only have 1 free variable to build the eigenvectors. Here we still have multiplicity 1 and 1 degree of freedom. You always have at least 1 degree of freedom when you're building eigenvectors, but as you saw above, sometimes you have 2. And that can happen when you have multiplicity 2, but not always, as you see in this example B. Another way to look at the mismatch is you see this E is an eigenspace, and these two vectors are linearly independent and they span E, so they form a basis. So the dimension of E is equal to 2, whereas in this case the dimension of E is equal to 1. So the dimension of the eigenspace matches the multiplicity of the eigenvalue. In this case, the dimension of E is 1 in both cases. So there is a mismatch between the dimension of the eigenspace and the multiplicity of the eigenvalue in this case right here. When that happens, we say that B is a defective matrix. So as you see, there's an interesting relationship between the dimension of the eigenspace and the multiplicity of the corresponding eigenvalue. So let's write this as a theorem. So let lambda be an eigenvalue. For a matrix A, with multiplicity m. So m is a multiplicity of the eigenvalue lambda. On the other hand, let E be the eigenspace. For lambda, the set of eigenvectors for lambda. Then the dimension of the eigenspace, first of all, has to be always at least 1. There's always at least one free variable when you find the eigenvectors, because they have to necessarily be non-trivial. But you cannot have more than m degrees of freedom, where m is a multiplicity of the eigenvalue. So, but the dimension can be anywhere between 1 and m. So first of all, you know that to prove this, that the dimension of E, as I said, has to be greater, or at least 1, because E is a non-trivial vector space. But the dimension of E is also bounded by m. Because the dimension of E is the number of free variables. In the solution of A minus lambda I V equals 0, which cannot exceed the number of equations that you have, which is bounded by the multiplicity of the eigenvalue lambda. So as we saw in the two examples, you have different situations. So a matrix is non-defective if for every single eigenvalue, the dimension of the corresponding eigenspace equals the multiplicity of the eigenvalue. So if the dimension of E equals m for every eigenvalue. So the matrix A that we had in the previous example is an example of a non-defective matrix. And conversely, a matrix is defective if the dimension of an eigenspace is less than m for at least one of the eigenvalues. And so, for example, matrix B that we saw on the previous page is defective. So a corollary of this last theorem concerns a special case where a matrix has, an n by n matrix has n distinct eigenvalues, which means all the eigenvalues are different from each other. There's no repeated eigenvalues, so they all have multiplicity 1. In that case, all the corresponding eigenspaces have dimension 1 because 1 is the minimum, and the matrix is non-defective. So if an n by n matrix A has n distinct eigenvalues, so distinct meaning that lambda 1 to lambda n are all different, which means all of them have multiplicity 1, then all the corresponding eigenspaces have dimension 1. Because 1 is the minimum, and A is therefore non-defective. So if all eigenvalues have multiplicity 1, the matrix is necessarily non-defective. So furthermore, in this particular case, eigenvectors that provide from different eigenvalues will be linearly independent. So this last part of the corollary here we can prove by contradiction. Which means we can prove by assuming that the distinct eigenvectors are linearly dependent and arriving at a contradiction. So instead of doing it here, I'll just post this proof on Schoology. Make sure you look at it so you can study how it goes. So finally, I'm going to finish with two other theorems that are extremely important. We saw the proof of the first one in the special case of a 2 by 2 matrix already in class, but it's worth mentioning that this is a general theorem. So if you have the set of eigenvalues, lambda 1 to lambda n, be the eigenvalues of A, and this is counting multiplicities. Which means if one of these eigenvalues is repeated, you need to count it twice. Then the sum of these eigenvalues, which you can write the sum of the lambda i's, is equal to the trace of the matrix. And the product of these eigenvalues, which you can write as the product with the capital operator pi, is equal to the determinant of the matrix. And this is valid for any n by n matrix A. Finally, another theorem that concerns eigenvalues and eigenvectors relates to Markov chains. So a Markov chain is of the form x to the n plus 1 equals pxn This is a Markov chain where P is a transition matrix. And the transition matrix of a Markov chain is necessarily stochastic. Meaning that the column sums of all the elements always equals 1. So then the long-term state vector, x infinity, so if it exists, it satisfies x to the infinity equals px infinity. Which means that when the system reaches its steady state at the long term, the state vector does not change from one time step to the next. So you have this equation right here. You can also view this as the definition of an eigenvector and eigenvalue. This simply shows that x infinity is actually an eigenvector of p corresponding to the eigenvalue of 1. Eigenvector of P corresponding to the eigenvalue 1. So if you have a Markov chain, the transition matrix, because of its property of being stochastic, also has the property that at least one of its eigenvalues will be equal to 1, and the corresponding eigenvector will be the long-term steady-state vector of the Markov chain.